So let's start with the visual analytics cycle, like the traditional one. Yeah, as you maybe all know, visual analytics can be described as this cycle. It starts with a data set that's going to be transferred and somehow integrated into a data set that you can handle. Then there is, you can either transform that into a hypothesis, which is any concept that you can use to analyze your data. It can be transferred into visualization, so any concept that you can use to visualize your data. You can go back and forth between those two concepts. So usually those are interconnected, and it's not, one doesn't really, or it's very seldom that one comes without the other one. And by doing that and working through that cycle and providing interactive mechanisms, you can create new insights that you can usually feed back into the cycle again. And what we're usually doing is we're making a cut in the cycle and saying, okay, the first part, this is the system, and the second part, this is the human, which makes completely sense because creating insights is something that goes on into the mind of the user. Yeah, so there's one important thing when we're talking about this data component, and in this data component you can have different operations, and these are maybe you have to transform your data, maybe you have to clean your data, you have to select parts of your data, and in many cases, and this is very specific for biomedical applications, I would say, you also have to integrate your data. So they're usually coming from different sources, they're in different formats, there are different types of data, and this is usually a big problem. So data integration, as I said, is really the big thing, because if we're looking into biomedical data, we can have very different types of data. We can have like some sheets that are giving you some numbers, some things that we measured. We can have medical images, we can have molecular data, we can have measurements that are going over time. And those are, from a computer scientist point of view, all different types of data that we all have to handle somehow. And in a perfect world, we would handle them all together, because if we would handle them all together, we would maybe get more insights. So that was a recap on visual analytics in general. And now I want to come to the point where we are talking about uncertainty aware visual analytics and why this is so important. So I want to give you a little teaser. So what is uncertainty if we're really looking at it at a practical way? So you're seeing this picture of sloths and chocolate croissants, and in our mind, those are two really different things. But if you're looking at those images, they don't really look that different anymore. And even worse, I just added like a Gauss blur on it. If you're looking at this one, I would swear by everything that I have that this is supposed to be a sloth, but it's not. So it's really important to think about uncertainty. So after the fun part, here comes the technical part. So what is uncertainty technically? So uncertainty is a doubt of a measurement. And there are a lot of people that misunderstand or classify uncertainty with an error. An error knows a ground truth. And if you're measuring something and you know what you should have measured and you know what you measured, then you have a distance between those two things. And this is an error which can be completely easily quantified and computed. On the other hand, you have uncertainty, which is just a doubt. I mean, it's like you measured something, could be true, could be not. You don't really have a ground truth. And so it goes like you have those measurements and you're like, okay, are they true, are they not? And there are two very prominent ways on expressing this uncertainty. One is you just give a boundary and be like, okay, I have something measured and it's plus minus something. That's not what happens when you have some measurement instruments. They're usually coming with those boundaries and be like, okay, what I'm measuring could be true, plus minus, whatever. And then there is another way on expressing that with a probability distribution, where you just say, okay, I measured something and there's a good chance that what I measured might be true. And the further away I'm going from what I measured, the less probable it will be. Uncertainty events can have a lot of different properties. So what I'm doing in my research is really like, what are all those uncertainty events? How can we classify them? What are different types that can happen? And the first thing that we are trying to do is, how can we describe uncertainty events? So uncertainty events to have a type, a quantifiability, can be or cannot. This event can have dimensionality, a category, a continuity, and a quantification strategy. And due to time restrictions, I will just talk about the type and the quantifiability today. So for the type, there are actually four different types, or at least let's say from the leaves of this graph here. You can either have objective uncertainties and subjective uncertainties. Objective uncertainties separate into two groups, aleaphoric and epistemic. Aleaphoric uncertainties arise when you run an experiment different times. So you can take ball and drop it down on the ground and measure how long it takes until it hits the ground. And you will have, every time you're doing that, different measurements. They are small, but there are different measurements because there are side effects that you cannot really handle in that. If maybe someone opened the door and there's a little bit of wind or whatever. And then there's epistemic uncertainty, which arises from the model, because models by definition are not complete. They approximate things, they have boundary conditions, and so on and so forth. On the other hand, we have the subjective uncertainties, which are a little bit harder, because there's on the one hand rule uncertainty, where the question is this rule correct? Is it correct what we're thinking might be a rule? And then there's moral uncertainty, which is another level of this rule thinking. You know the rule is correct, but you're asking yourself if it's ethically correct to apply this rule. Like, you know, we have the rule of doing this and that, but you feel like it's wrong to do it for whatever reason. So what is uncertainty when we're dealing with life sciences? We saw that we have all those different types of data. And when we're really going down and break down all types of data that maybe we know, or let's say the biggest groups of data that we know, we can have, for example, spatial data. And in that spatial data, you can have different types of uncertainty. For example, you can have the values that you have in your spatial locations might be wrong. The locations itself might be wrong or are affected by uncertainty. Then there's graph data, which also comes with different types of uncertainty. Does the node exist? Do the connections between nodes exist? Do the values that are stored in a node, are they correct? And for field data, it's also like the field itself might be shifted. There's usually a position where this field is located at. And then in all the different cells and fields, the values might be affected by uncertainty. Same goes for high dimensional data. You can have uncertainty in each of the cells. And for time-dependent data, you can have the values, either the values could be wrong, or like the time points where those values are stored might be affected by uncertainty. And for document data, each of the characters can be affected by uncertainty. So what I'm doing in my research is trying to really break this visual analytics cycle down and be like, okay, what types of uncertainty can be inherent in each of those nodes in the visual analytics cycle? So for example, in the data set, we can have incompleteness of data, happens all the time. We can have finite instrument resolution. Those are examples that can happen in the data set. For the hypothesis, there's incompleteness of the model, for example, parameter uncertainty, and so on and so forth. And for visualization, this goes a lot with how are we actually visualizing our data? Like what is the mapping strategy that we're using? What is the integration that happens when we're displaying something? And the thing is, why am I showing you this table? Because we can now see what type of uncertainty we're talking about. And what we can also do is we can quantify or we can express the level of quantifiability. I don't want to go into too much detail, but level 1 uncertainty would be, okay, I know everything about this uncertainty and that's fine, and I can handle that, and we're fine. And level 5 would be, in no circumstances in this world, not even if we would all be like Newton and would invent all the coolest, newest stuff, we could never, ever take care of this uncertainty. So the cool thing is, as those are all the system parts of our visual analytics cycle, is there is hope. We can somehow deal with this uncertainty. But now comes the human part, and that's a problem because we cannot quantify that. With our knowledge about human cognition and how people are understanding data and process data is so limited that we cannot really understand how all those uncertainties that are happening there come together and can be expressed or somehow can be dealt with. So what I did is I reconstructed the cycle a little bit, because when we're looking at the original cycle, there's a lot missing. It's not technically not able to really deal with those uncertainties. And the thing is, each of those components, as we've seen that before, introduces uncertainties. So I thought, okay, maybe we need some more nodes in there. Okay, so now that we have this cool cycle, I think it's cool. The question is, how do we go from there to there? And what I'm doing recently is I try to find a workflow where we can go from a visual analytics cycle to an uncertainty visual analytics cycle, because there are strategies that give you directions on how to create visual analytics cycles for all types of problems. So I thought it might be a good idea to start there and then just extend it with some steps that I created. And the first step is just quantify all types of uncertainties in all the components. And that's what I made those tables for. Because if you're looking at those tables, you can say, okay, that's an uncertainty that I need to be aware of. This is an uncertainty that I need to be aware of. Okay, this one is not really needed in my case. And then you can just go through all the uncertainties and just quantify those uncertainties if it's possible. As I said, in the inside, there's a little problem still. Then the next step is exchange your original components by uncertainty strategies. And what we're doing also right now is we're writing a start that where we're summarizing all those things that you need to exchange and give you options on what can you exchange with what. Because as I said, for segmentation, for example, there are uncertainty-aware segmentation approaches. The question is just, what do you want to use for that? Because there's not only one. And for the next step, it says, separate your feedback loop, make sure that you're aware of what comes directly as an insight with an uncertainty attached and whatnot. And the last part is the provenance that I've been talking about. So find strategies that track down all the uncertainties when you're running the cycle, when you're creating new visualizations, when you're adapting the visualization, when the user is interacting with it, and so on and so forth. So, okay, that was the theoretical part. I want to show you some really cool applications that we recently made. And the first one, which is right now my favorite project that I'm having, is the stroke lesion analysis. And I first want to talk about the problem itself. So when you are having a stroke, what happens is that one of your vessels in your brain gets blocked by a plug, and for a certain amount of time, it depends, sometimes it's just some seconds, sometimes it takes longer, parts of your brain cannot be supplied properly anymore. And what can happen through that process is that parts of your brain are dying, and this is where like people get disabilities or can also die from. In general, strokes are the second leading cause of disability worldwide, so this is like really a problem that you should think about and take care about, and it will become worse and worse as people become more older, and let's say in modern civilizations, people are smoking too much, drinking too much, and so on. And what happens when you have a stroke, or if a doctor thinks you have a stroke, you're coming into the clinics and they're going to do different CT scans. For example, usually they start with a normal CT scan. Then they do a CT angio, which means they give you contrast bolus that highlights the vascular system in your brain, because then you can see, okay, is there a vessel that is occluded? And for the last one, it's the CT perfusion, which is also with a contrast bolus, but it works a little bit different because this goes into your tissue and shows how much perfusion happens in this tissue. And from those images, you can see there's a stroke or not. But what you cannot see in that specific moment when you're coming to the clinics is what part of the brain will actually die, because this is something that develops over time. It takes like almost half a year until a patient reaches the point where a lesion doesn't really go back or becomes worse, whatever. And what we are having is we're having super awesome database from the University Hospital in Leipzig, where we have over 300 patients, where we know this incoming images. And we also know a follow-up from half a year after that, where we really know how does the lesion look like. The fun part about that is we have this ground truth that is labeled by the collaborators that we have in 3 different versions. So every patient is labeled by 3 different clinicians, and they do not agree all the time. So we're having a fuzzy ground truth here, which is challenging. And what was the initial idea of us was we're using a CNN or a specific CNN, a so-called UNet, and give an infarct risk map that predicts what might be the lesion in half a year. So as I said, we're using this unit. I'm not sure how much you're aware of the concept of a unit, a specific neural network that can do segmentation tasks. Let me put it like that. And the thing is, there's also the question, there is a very, very expensive, not only in terms of money, it's also in terms of resources that you're needing from the hospital and risks that is coming or risks that are going into the direction of the patient. Like it's an 8-hour operation and it takes a while. And the thing is, when is it necessary or when does it make sense to use it? Because there are some measurements that they have that tell, okay, we should do that procedure now. And for some reason it works and sometimes it doesn't. So they said, okay, those measurements are actually more or less guessing. Can we do that better? And what we did is we used this neural network and made 2 different options. One of the networks is trying to simulate what happens if you're doing this procedure, and one of those networks is trying to simulate what happens if you're not doing this procedure. And what can happen is, for example, here, you see how we can predict the lesion. And the interesting thing is, this is the difference. This is what the network said would happen if you are doing the procedure. This is what the network said would happen if you're not doing the procedure. So you can compute the difference. And if the difference is large enough, this is an indicator that you should do this procedure. And what we're doing soonish is that we're going to have a clinical trial if we're really on the right way there. Because we can try this out. We can just take the images and see and let them do their surgery as they are planning it, as they have their scale. And we can run our network and be like, just monitor it and see, can we do that better? Can better predict to do this procedure or not? What we also do is for the evaluation of neural networks, you're usually having this like true positive, false positive, true negative values where you can compute different measurements and be like, okay, my network is accurate in this and that sense and under this and that measurement. And the thing is, those hard thresholds are actually not cool. Because you're using this threshold, we're arguing with our clinical experts about what is actually the best threshold, and then they're like, I don't know. So we are using some random threshold where we are not sure if this threshold actually makes sense to evaluate our network. And what we did is we adapted our measurements so that we're actually like using a Gaussian distribution function over the threshold and be like, okay, when you're close to the threshold, no matter on what side you are, then you're still considered somehow in our computation of this is a true positive or a true false positive and so on. And then you can really have this visualization that tells you, okay, when I'm manipulating my Gaussian distribution function and be like, it's going to be more broad, then you're going to have these fuzzy transitions between like the true positives and the false positives. And this is what you can do with all of the 4 classifications that you have. And using those pre-computed classifications, you can have also a damping factor. For example, if you can have units that also give you an uncertainty quantification of the result. And let's say we are using this result and we have values that have higher uncertainty than others. Then we do not want to make them so important in our computation of is this network accurate or not, because it doesn't make sense. This value is completely uncertain. Why should it have an influence in the same manner as a value that has no uncertainty, for example? And then you can manipulate those functions and be like, okay, I can have these damping factors, and the higher the damping factor, the more you're not considering uncertain values. And then you see how those evaluation functions of the neural networks are changing. What we also did is, as I said before, we have this multi-model input with different types of CT scans. And the thing is, usually doctors just look at one of them. In fact, they actually just look at one slice of one of them. And what we try to do is make a visualization that combines all different aspects of this free imaging that I showed you before. For example, we have some anatomical context, we have the vascular system, we have the perfuted tissue of the brain, and we also have like the lesion. And you can set these cutting planes, you can have different interaction opportunities, and then you can understand how those different types of data are correlated to each other. What we also did are some first experiments on how can we understand the provenance of our segmentation procedure, for example. Here we're working with not with a neural network, but with a fuzzy segmentation algorithm. And what we can do is we can also extract an isosurface that has the surrounding surface that indicates how this might be displaced, this isosurface. And those are like two steps. So in the first step we have, or in the original data, we have an uncertainty histogram. We made an uncertainty quantification for that. And what happens after the segmentation, the histogram changed. So also the average of the uncertainty changed. And what happened after the isosurface extraction, also the histogram changes. So you can follow a little bit on what's going on in your uncertainty histogram. Okay, what are general open problems when we're talking about uncertainty-aware visual analytics? So we saw a lot of examples. I taught you a little bit about the concept. And there are two types of open problems when we're thinking about uncertainty-aware visual analytics. And one type is resulting from the visual analytics cycle itself. So this has nothing to do with uncertainty. I mean, it doesn't go away when we're considering uncertainty, but it's not coming from the point that we're taking care of uncertainty. So we need a proper description of insight, as I said. We don't know what's going on in the human brain. We need an approximation of the amount of knowledge that is generated by a visualization, which goes in the same direction. So that's also something that we really have to research. And then there's the other class of problems that's more into like resulting from the consideration of uncertainty. And here the problem is, when do we actually need this uncertainty-aware visual analytics cycle? There are problems where we do not need that. We have to be fair at that point. But what are they? We need a survey, as I said, we're working on that, of existing techniques so that people know that's what I can exchange and that's how I should exchange it. There is no nice framework for uncertainty visualization. We all know about BTK and ParaView, and I would love to have a framework that works in a similar way just for uncertainty visualization, because you can, of course, take care of uncertainty with BTK and ParaView, but you somehow have to build up your own new visualization, and that's not what I mean. We have to teach more about those principles. Every time I'm talking to to some new person from the clinics who is interested in working with me, I'm like, well, how about uncertainty? We don't take care about uncertainty. And then they're starting talking and be like, oh yeah, and I have this data, and then here, well, we have these ground truths and they do not match together. And I'm like, you are talking about uncertainty. But the thing is, they just don't know the word, or they just don't know what that word means. And we have to teach that. Yeah, we have, of course, take care of the approximation of knowledge uncertainty. And what I'm also interested in researching the link to ensemble visualization, because I have the feeling that you can transform uncertainty problems into ensemble problems and back, of course, with loss. But then you have two worlds where you can grab from all the techniques that are out there. All right, thank you for your attention. I'm open for questions, and feel free to contact me if you wish.